Alright, silly people, here's the situation. You know how the classical harmonic oscillator uh, classically could not go outside of like its maximum length, like if it's a spring with an outstretched length of L, uh, the end of the spring can never go outside of uh, that length. It can't be over here. Um, that's not the case for the quantum harmonic oscillator. Um, in fact, there is a non-zero chance for any old harmonic oscillator eigenstate um, to be found actually outside of the classically allowed zone. Um, so, what am I talking about right now? If you look at the ground state wave function of the simple harmonic oscillator, you have that it's m omega over pi h bar to the 1/4 um, times what e to the minus m omega over 2 h bar x squared. Um, if you want to calculate the probability that you find the wave function anywhere, um, you'll so the probability that uh, the particle exists given this wave function is just the integral over all space uh, of this wave function dx, which we know is equal to 1 because the wave function exists. But if we wanted to find the probability that the particle is outside of the classically allowed zone, then we have, first of all, the integral over all space of the square modulus of the wave function, but then minus the integral of just the classically allowed region, where I can say it's minus x naught psi 0 squared dx. And so what are the classical turning points? They're found by setting the energy equal to exactly equal to the potential energy. So that's just going to be, for the harmonic oscillator, m omega squared x squared, where I'm going to find x0 there, over 2, and then I'm going to solve for x0 so that we have just 2e over m omega squared with a plus or minus sign attached to it, depending on which side of 0 you're on for the position, so plus or minus. So looking at that, the probability that we find the particle outside the box is actually just 1 minus the integral, and I'm going to write a big integral sign, between minus this value, so minus root 2e over m omega squared, to 2e over m omega squared of the square modulus of the ground state wave function, which is just the square root of m omega over pi h bar times e to the minus m omega over h bar x squared dx. All right, that'll give you the probability that the particle practically tunnels through the wall. So here I have a Desmos screen with the same stuff set up as before. This function at the top will calculate that integral that we were doing numerically because it can't be done analytically. And it gets a value of about 16%. So 16% chance you find your harmonic oscillator outside of the classical uh, bounds. I will make a note that I used the energy value of the ground state harmonic oscillator, which is just h bar omega over 2 um, for that. And I put in all these sliders for m omega and h bar just to make sure it wasn't like an artifact of given values of m omega and h bar. Uh, but it seems that with them changing, uh, that the probability remains constant for the harmonic oscillator to tunnel. So yeah, cool stuff there.